In our previous lecture, we introduced two symmetric positive semi-definite matrices, namely reachability Gramian and controllability Gramian, and established their link to the controllable reachable subspace and controllable subspace, respectively. In this hour, we will concentrate on the special but very important case, namely the LTI case, and we will introduce yet a third matrix, which we will call the controllability matrix, and study its relation to the subspaces, reachable and controllable subspaces, and also the Gramians that we talked earlier. Okay. So now we're considering the LTI case. Okay. Therefore, the system that we will study is x that equals ax plus bu. And suppose that the system is of order n, and the size of the input vector is, let's say, k. Okay, so u is a vector in Rk. Now, for this system, the Gramian matrices become simpler. So let's figure them out. The Gramians, reachability and controllability Gramians, they become following. Okay, this is our reachability Gramian. Okay, for the given interval t0 to t1, t1 larger than t0. So that can be written as t0 to t1 e to the a t1 minus tau b transpose e to the a t1 minus tau d tau. So here we have transpose. Okay. So that's our reachability Gramian. By construction is symmetric and positive semi-definite. It's positive semi-definite because it's the integrand is something times its transpose. And as for the controllability Gramian, we have a similar but a little bit different matrix, or the integral. This time we have e to the a t0 minus tau b transpose e to the a transpose t0 minus tau d tau. Okay, and these boil down to, okay, by a change of variables, it can be written in this following simpler form: from 0 to t1 minus t0. This is the length of the interval, which we will see for an LTI system has no significance from the controllability or reachability point of view, as long as it's clearly something non-zero. E to the a t b transpose e to the a transpose t dt. Okay, and as for the controllability Gramian, we have, or we can write the following integral. Okay, e to the minus a t b transpose e to the a minus a transpose t dt. Okay, now these are two symmetric positive semi-definite matrices, and now we're going to introduce yet a third matrix. So we now define the following matrix. Since it's important, it has a name, and it's called the controllability matrix. Okay, the controllability matrix. Okay, usually denoted by C, and it's an n by and k matrix. Okay, so it has n rows, n being the order of the system, and nk columns. Okay, k being the size of the input vector. If you have a scalar input, then it becomes a square matrix, but in general, it's not a square matrix. Okay, so we define the controllability matrix C, or we construct the controllability matrix C as follows. So C is constructed as the first k columns are the columns of the B matrix, and then the next k columns are A times B, okay, or the columns of that matrix A times B, and then the next k columns are A squared, the columns of A squared B, and so on. Okay, A squared B, and you go until n minus first power of A. Okay, A n minus 1 B. Okay, so this is therefore an n by nk matrix. Okay, and now what we're going to do in our next result, we're going to investigate the relation of, or certain properties of this matrix, okay, in relation to the reachable and controllable subspaces, okay, or in particular the reachable and controllability gramians. Okay, so remember that earlier in our previous lecture we have made the link between reachability gramian and reachable subspace, which was that the range space of this matrix is no other than reachable subspace, and the dual result was the range space of the controlled matrix is the controllable subspace. Okay, and now we're going to combine all those results into a single theorem, which is valid not in general but for the LTI case only. Remember that our previous results for the general linear time varying situation. Okay, this is the theorem that we will now talk about. For any time instance T1 and T0, T1 later than T0, we have the following set of equalities. Okay, so the range space, the reachable subspace for the interval T0, T1 equals the range space of the reachability gramian T0, T1 okay, and we have what? We have the range space of controllability gramian from T0 to T1 equals the controllable subspace for the interval T0 to T1. So these equalities we have already established, and they are true for the general case, the LTV case, linear time varying, for linear time varying systems. Now what we do is we combine those two separate equalities and make it into a single one, by where the connection is established by the controllability matrix. So this equals the range space of the controllability matrix, and that equals the right hand side. Okay, now there's an important thing to emphasize. Note that reachable subspace and likewise the range space of the reachability gramian, they by definition depend on T0, T1, or this interval. Okay, and that's important for the LTV case, but this matrix is a time invariant matrix. Okay, therefore it has nothing to do with the interval from T0 to T1. Therefore it means that for all intervals T0, T1, provided that the length of that interval is non-zero, the range space, the reachable subspace and controllable subspace are the same for an LTI system. Okay, now let's present a part of the proof, okay? Because the other part is very similar to the part that we will talk about, so it will be left as an exercise. So what we're going to show is the following. The reachable subspace for the interval T0, T1 equals the range space of the controllability matrix. Okay, and to show equality, what we do is first we show that one of the sets is a subset of the other, and in the second part we show the range space of C is the subset of reachable subspace. Therefore, if both are the subsets of each other, we will have shown the equality. Okay, so range space of C must equal the reachable subspace, and this equality was already established, and that it's true for even the general case LTV. Therefore, this part here will have been established at the end of our proof, and the other part, the second half, is very similar. So we will omit it. Okay, so let's therefore begin with this subset relation. And to show that, what we will do is we will start with an arbitrary element in this reachable subspace, and we will show that that arbitrary element must necessarily be an element of the range space of the controllability matrix 2. Okay, so let's proceed with that then. So let us start with an arbitrary element from the reachable subspace, which we call it x1. Let x1 belong to the reachable subspace from T0 to T1. Okay. Then, by definition, we can find an input such that when you start the system from the origin and apply that input to the system, at the end of the interval at T1, you reach this point, x1. Okay, so that's the very definition of reachability. So let's write that down. We can find the control input. Let's call it u of t, such that x1 equals, okay, state transition matrix times the initial condition, but by definition of reachability, we take the initial condition to be 0. Therefore, we only have the integral term due to the input. So we write x1 equals from T0 to T1 e to the a T1 minus tau bu tau d tau. Okay. Okay, once again, we start with an arbitrary point from the reachable subspace, and by definition of reachable subspace, there must exist an input u such that x1 equals that expression. Okay, physically speaking, starting from the origin, you can find an input which drives the state from the origin to the point that belongs to that reachable subspace, which we're denoting by x1. Okay, now remember the infinite series definition of the state transition matrix e to the at. It was identity plus something times a plus something times a squared and so on. So therefore, e to the at can be written as an infinite polynomial of powers of the A matrix, okay? And we know from 501 that by Cayley-Hamilton theorem, any power of a matrix can be written as a linear combination of its first n minus first powers, where n is the size of our square matrix. In this case, the square matrix that we're talking about is A, and its size is n by n. Okay, so by therefore Cayley-Hamilton theorem, there exist scalar functions, okay, which allow us write e to the at as a linear combination for each time, linear combination of its first n minus first powers. Okay, functions alpha I t such that e to the at equals I equals 0 to n minus 1 alpha I t a raised to the power I. And by definition, the 0th power of any square matrix is the identity matrix. Okay. Now, combining that observation by this expression here, which indicates that x1 belongs to the reachable subspace, we can write the following. Okay, hence x1 can be written as, okay, now what we do is we replace this e to the a t1 minus tau term with this expression, a summation, okay, of the powers of a to the I. And then we have the integral of some summation, and that can be written as following. x1 equals b ab an minus 1 to the b, okay, times this vector, okay, of n k by 1. N is the order of our system, k is the size of our input vector. And now we have t0 to t1 alpha 0 t1 minus tau u tau d tau. Okay, and then we have here t0 to t1 alpha 1 t1 minus tau u tau d tau up to the n minus first power t0 to t1 alpha n minus 1 t1 minus tau u tau d tau. Okay, so x1 can be written as this matrix, okay, times this nk by 1 vector. Okay, now this matrix we immediately recognize is no other than the controllability matrix. So this is RC. So what we have obtained is the following. No matter what x1 you pick from the reachable subspace, that x1 must always be able to be written as C, the controllability matrix, times something. And then by definition of range space, it automatically follows that x1 belongs to the range space of the controllability matrix. Okay, so x1 belongs to the range space of the controllability matrix. Okay, therefore this direction has been shown. Now we're going to show the other direction. That is, we will start with an arbitrary point from range space of C, and then we show that a vector must necessarily belong to the reachable subspace, and that will give us the fact that range space of C must be a subset of the reachable subspace, and then since both are the subspace of one another, we will have shown that two subspaces are the same subspaces. Okay. Let's now move on to the other part. Okay, part 2. Range space of the controllability matrix is a subset of the reachable subspace. Okay, so we start with picking an arbitrary vector from the range space of the controllability matrix, which we denote by x1. Then, by definition of range space, we should be able to find a vector V, okay, a vector of size n times k. Remember that matrix C, controllability matrix, was an n by nk matrix, okay, such that x1 equals controllability matrix times that V. Okay, so that means x1 belongs to the range space of the matrix C. Now, we proceed by choosing an arbitrary vector eta 1 from the null space of the reachability Gramian. Okay, reachability Gramian for the interval from t0 to t1. Okay, then we can proceed as follows. 0 equals reachability Gramian WR matrix times eta 1. So this means that eta 1 belongs to the null space of the matrix W of R. Okay. Now this is a vector of size n. This is an n by n square matrix. Therefore, this 0 is the 0 vector of size n. Now what we do is we multiply both sides with the transpose of eta 1. Okay. And now this is eta 1 transpose times this was 0. Therefore, clearly this is 0. Excuse me. Now, but this time 0 is scalar 0. Now, that equals what? Remember the integral definition of the reachability Gramian. Okay, and now that integral is being multiplied from left and right by eta 1 transpose and eta 1. Since eta 1 is a constant vector, we can squeeze them inside the integration, and we can write the following: eta 1 transpose e to the a t b transpose e to the a transpose t eta 1 and then dt. Okay, and this can be written as from 0 to t1 minus t0. Note that here we have something transpose times something, so that's the norm square of that something. So we can write therefore b transpose e to the a transpose t eta 1 norm square dt. Therefore, this term must equal to the integral of some norm square function. Okay. Now this function is continuous and it's norm square. Therefore, it's never negative. So it's a non-negative. It's a non-negative function. It's continuous, and we're integrating that and obtaining 0 as a result. So that's only possible if this thing is identically 0, okay, throughout the interval of integration from t0 to t1. So therefore, that allows us to write the following: eta 1 transpose e to the at times b is 0 for all times from t0 to t1. Okay, so the norm must be 0, therefore what's inside norm must be 0, and then what we did is we simply transpose that 0. Still we obtain 0. Now this is true for all times, okay? Therefore, this is constant, clearly, which means that its derivative must also be constant. So what we do is we differentiate this with respect to time. The only thing that's varying with respect to time is the state transition matrix e to the at. Derivative of e to the at is a times e to the at, and we obtain eta 1 transpose a e to the at times b equals 0. Okay, which we obtain by differentiating both sides. Again, the same trick. This is constant, therefore its derivative must be 0. That produces eta 1 transpose. Now we differentiate e to the at once again, so it brings another a. So that means we have a square e to the at b equals 0. Okay, again, what we did, we differentiated. And we're using the property that derivative of e to the at is a times e to the at, or e to the at times a, because those two matrices commute. Anyways, we keep doing this until the n minus first power. Okay, and we write eta 1 transpose a raised to the power n minus 1 times e to the at times b equals 0. Okay, and then these are all true for the times from the time t equals 0 to t equals t1 minus t0. Okay, therefore, at t equals 0, therefore they must also hold true. And if you plug in t equals 0, what you obtain is e to the at valued at t equals 0, which is identity. Here we have another identity and so on. And all those e to the at's can be simply removed because they become identity at t equals 0. Okay, at t equals 0, e to the at is by definition identity matrix, which allows us to write the following set of equations. Eta 1 transpose times identity times b equals 0. Eta 1 transpose times a times b equals 0. And so on. Eta 1 transpose a n minus 1b equals 0. Okay? This n equations can be written as a single equation, and if you do that, again the controllability matrix pops out. Okay, so eta 1 transpose times b, ab, a n minus 1b, therefore must equal to 0. So what we have obtained is that eta 1 must belong to the null space of the transpose of the controllability matrix. Okay. So here we have the controllability matrix C. Now how to proceed from this point? Let's see how that goes. Okay. Hence, to summarize, this is what we've obtained. Eta 1 transpose C equals 0. Okay, once again, what eta 1 was it was just an arbitrary vector that belongs to the null space of the reachability Gramian. And we show that that vector, that arbitrary vector, must necessarily satisfy this equation, eta 1 transpose times C equals 0. Now, eta 1 transpose times x1. Let's look at this inner product. Eta 1 is an arbitrary vector from this null space, and x1 was an arbitrary vector from this range space of C. So this inner product, therefore, equals eta 1 transpose times. Since x1 is in the range space of the controllability matrix, there exists some v, which produces x1 equals cv. Okay, so let's replace x1 by that expression c times v, and then immediately this appears, eta 1 transpose times c, which we have just shown to equal 0. Okay, so that equals 0. So that implies what? Now, since eta 1 was an arbitrary vector from the subspace, and x1 is orthogonal to eta 1, so that means x1 is orthogonal to any vector from that subspace, which is the null space of the reachability Gramian. Okay, so that means x1 must be a member of the orthogonal complement of this subspace. Okay, so x1 therefore must belong to the orthogonal complement of this subspace. Okay, so that means x1 belongs to, since this equals to the range space of the transpose of this matrix, we have x1 must belong to the range space of the reachability Gramian transpose. And then we remember that reachability Gramian, this matrix, was symmetric, therefore it equals its transpose, so that equals range space of the reachability Gramian. And then from the previous lecture, we remember that range space of the reachability Gramian is no other than the reachable subspace, okay, for our system. So that means no matter what x1 you choose from the range space of C, that x1 must belong to the reachable subspace. Hence, that establishes that this subspace is a subset of the reachable subspace. And then in the previous step, we have shown the reverse direction. Therefore, this and that, those two sets must be identical. Okay, they must be the same set. Okay, so that therefore establishes range space of the controllable matrix equals the reachability Gramian. Okay. Okay. The other direction can be shown similarly, and therefore it's left as an exercise. Okay, for those for those of you who have time. Okay, now let's apply our latest discovery to an example, simple circuit that we have studied already in the past, and see what controllable matrix tells about that example. So we revisit the RC, parallel RC network. Okay. Network revisited. So this was our circuit. We have a voltage source, which is our input, that's driving two RC loads that are in parallel. Okay. R1, R2, C1, C2. Okay, let X1 denote the voltage of the first capacitor and X2 the voltage of the second capacitor. And this voltage supplied by the source is our input to this system. So we have obtained the state space representation for the state choice X1, X2 as X that equals AX plus BU, where A and B matrices were minus 1 over R1 C1 0 0 minus 1 over R2 C2, 1 over R1 C1 and 1 over R2 C2. This is our A matrix and that's our B matrix. And we have studied not the general case but the special case where two time constants were equal. R1 C1 equals R2 C2, and then we figured out that in that case the reachable subspace and also the controllable subspace is a one-dimensional subspace that's spanned by the vector 1 1. Okay. Now by the help of controllable matrix we will now restudy this example for the general situation where the resistance and capacitance values are arbitrary. Okay, so let's construct for the system the controllable matrix. This is our A, this is our B. Okay, controllable matrix. C is B, AB, A square B, A cube B, and so on. You stop at n minus first power. Now for our system, n is 2. The order of the system is 2. Therefore, where you stop is A 2 minus 1, 1. So you stop at the first power of A. Okay, so this is our controllable matrix, B and AB. Now, since we have a scalar input, this matrix is square controllable matrix. Okay, in general, it doesn't have to be a square matrix. And let's write the controllability matrix explicitly. Okay, the first row is directly the B matrix. So we have 1 over R1, C1, and 1 over, excuse me, first column is the B matrix, R2, C2, and the second column is A times B. A times B is very easy to compute because A is a diagonal matrix. So what we have here is minus 1 over R1, C1 square, and here we have R2, C2 square. So that's our controllability matrix. Okay. Now, we have shown that when R1, C1 equals R2, C2, that is when the time constants are equal, the controllable subspace is the subspace spanned by the vector 1, 1. So let's verify that result once again. If R1, C1 and R2, C2, they are equal, then what we have here is some vector with both entries the same, and here the second vector is also such that both entries are the same. Therefore, it's clearly the two columns are linearly dependent, and the range space, which is the controllable subspace or the reachable subspace, is the subspace spanned by the vector 1, 1. Okay, so that matches our previous conclusion. Now, how about the general case? If R1, C1 is different than R2, C2, if the time constants are different, then let's compute the determinant of the controllability matrix, which we can for this case because it's a square matrix. Okay, so determinant of the controllability matrix reads minus 1 over R1, C1, R2, C2 square plus 1 over R2, C2, R1, C1 square, which can be written as 1 over R1, C1, R2, C2 times this difference R2, C2. Okay. And then if the time constants are different, R1, C1 is different than R2, C2, then this determinant is non-zero. If determinant is non-zero, then this is a full rank matrix. If that's a full rank matrix or non-circular matrix, that means its range space is the entire space, which is R2 in this case. So different time constants, R1, C1 different than R2, C2, implies that determinant C is non-zero. And that in turn implies that C is full rank, or the range space of C is the entire space, state space, which is R2. Okay, so range space of C is the entire space. Okay, so that means controllable subspace and reachable subspace, because they are same for an LTI system, is the entire R2. So that means starting from the origin, okay, you can take any system, you can take the system to any point you like, and likewise, starting from any point, you can drive the state to the origin. Okay, combining those two facts gives us the following conclusion. Okay, if the time constants are different, then for all pairs of points x0, xf in state space in R2 and any time instance tf and t0, we can find an input voltage U of t that steers the capacitor voltage vector, okay, the capacitor voltages from x, T0 equals x0 to xtf equals the desired final step. Okay, so that was a that's a nice use of the controllability matrix for the simple circuit.